So in this video, we're going to be looking at how to graph rational equations, specifically how to find the components that are important to graph a rational equation. So in case you've forgotten, a rational equation is some function where you're dividing two polynomials. So I'm going to make this example up off the top of my head. X squared plus 3x plus 7 divided by, let's get weird with it, x to the 30th plus 16x squared minus 37. So this is an example of a rational equation. Thankfully, we're not going to be actually graphing this one. We're going to be graphing a few that I've chosen beforehand. But before we start graphing, we actually need to see what components we're finding and how to find them. So without further ado, let's go ahead and dive right in. So here are all the components that we're going to end up identifying. On this first bit, I'm going to just go ahead and show you what they look like, just in case you've forgotten. So if you understand what all of these terms are, then you can go ahead and skip a little bit. The horizontal asymptote is usually represented by a horizontal dotted line. An asymptote is an imaginary line that the function gets really close to but never actually crosses. There are some weird cases where you are able to cross a horizontal asymptote. So what this really is this talks about the end behavior of a graph. So it is possible to cross it, but at the end points, as x goes towards negative infinity and as x goes towards infinity, this is going to tell you about that end behavior. A hole in a graph, if I just draw any random function here, a hole in a graph is literally exactly what it sounds like. It is a physical hole that is created in the graph. Usually we'll represent that by an open dot to tell you that everything up until that exact point is determined. So if I say that this is at x equals 2, then at x equals 1.9999999, the function exists. At 2.000000001, the function exists. But at 2, we have a hole that it doesn't exist at. A vertical asymptote is the exact same thing as a horizontal asymptote in terms of how it's depicted and what it means. But this actually doesn't talk about end behavior. This is an imaginary line that the graph gets close to but never actually crosses. But it doesn't define the end behavior. It talks about what's going on in the middle of the graph or at some of the other points of the graph. Just as a quick reminder, a vertical line is graphed in the form of x equals some number, and then a horizontal line is graphed in the form of y equals some number. The x-intercept is, I'm sure most people already remember what it is, but I'm going to give you a little bit of the definition that's going to help us define it in the future. So if I've got, again, some random function, the x-intercept is everywhere it intercepts the x-axis. So for me, I actually have 3 points, 1, 2, and 3. And the x-intercept can be found at any location where the y-coordinate is 0. And that's a really important piece of information. The x-intercept happens wherever the y-coordinate is 0. That's the key to how we're going to find that in the future. If the x-intercept is where the y-coordinate is equal to 0, then the y-intercept will be the exact same thing, except it'll be where the x-coordinate equals 0. So let me again draw just a random function here. The y-intercept is going to be right here where we intercept the y-axis. Again, the x-coordinate will be 0. The y-coordinate will be some number. So that is a quick review as to what these components mean. On the next slide, we're going to talk a little bit about how to find them. So now that we know what they are, let's go ahead and see how to find them on a rational equation. So as a reminder, a rational equation is a polynomial divided by another polynomial. So one possible way to have that is ax squared plus bx plus c. So here's an example of a second degree polynomial. I know it's second degree because my largest exponent for my variable is 2. I've used letters because it's actually going to come in handy a little bit later. Plus it's to prove that it works for any numbers. A could be 1, it could be -1, it could be 6, it could be -6, it could be 60 billion. It doesn't matter, I'm just representing it as A. So we've got a second degree polynomial divided by a first degree polynomial, so d to the x. So here is a second degree divided by a first degree, and I could have something else off to the side here. Either way, it's still a first degree polynomial. So this is my first case that I'm going to actually use for my horizontal asymptote, because the horizontal asymptote depends on the degrees of your polynomial. So if the degree of your numerator is going to be greater than the degree of your denominator, then you're going to look at no horizontal asymptote. So if this exponent is larger than your denominator's exponent, then you're going to have no horizontal asymptote. Another potential case is going to be if you have the same. So if you've got ax, just to be weird, let's go to the third, plus bx divided by dx to the third plus e. So here's another third degree polynomial divided by a third degree polynomial. It doesn't matter what follows here as long as these variables have less exponent. So I could add in another coefficient here, sorry, another term where there's no variable in it. The degree is still to the third. So if these degrees are the same, if the degree of your numerator is equivalent to the degree of your denominator, then you actually do have a horizontal asymptote, and that's going to be at y equals, and this is why these letters were important. This horizontal asymptote, you're going to look at the coefficients of your largest exponent. So in this case, my horizontal asymptote will be at a divided by d. So if I had a 6 in the numerator and a 2 in the denominator, then it would be 6 divided by 2, which would give me a horizontal asymptote of 3. But again, this is why I left it as letters, because it really just depends on what you're given. You could also have -6 divided by 3 if this value was -6. It just depends on what those coefficients are. So leaving them as letters makes it totally allowed for any potential polynomial. The very last case that we're going to look at for horizontal asymptotes is if you've got the numerator has a lower degree. So ax plus b divided by cx, let's go to the fourth, let's be real weird here, plus dx squared plus e. So here we've got another one where the degree in the numerator is less than the degree in the denominator. So if the numerator is less than the denominator, we end up with a horizontal asymptote at y equals 0. So these are the three cases that you could come to in terms of your horizontal asymptote. The next thing we're going to look at is the whole and the vertical asymptote. Now most people would think that I would put the vertical asymptote next to the horizontal asymptote, but I actually look at it slightly differently. So the first thing you're going to do when you find both of these is find the domain of your function. And if you've forgotten how to find the domain, I'll show you how to do that in the example problems coming up, but it's a really good idea to be able to find the domain of functions. It's very important specifically for graphing these rational equations and for graphing other things in the future. So in order to find a whole, that's actually going to be where your domain restriction cancels. So this is kind of a weird statement, but if your domain restriction cancels, I have to stop talking for a moment to make sure I spell correctly. If your domain restriction cancels out, then you've discovered a whole at that location. So right now the statement might not make a lot of sense, but in an example problem you'll see what I mean by canceling out. And then by that reverse statement, if the domain restriction doesn't cancel out, then you're looking at a vertical asymptote. So if it doesn't, the domain restriction doesn't cancel out, that's when you're looking at a vertical asymptote. and you're going to have a vertical asymptote at x equals whatever that restriction is. The last two things we're going to look at are the x-intercept and y-intercept. This is actually the exact same thing that you saw in your other graphing classes, but the definition that we use to look at what these are is actually going to help us figure out what those are. Your x-intercept happens when y equals 0. So what you're going to do is set y equal to 0 and then solve for x. And that'll give you your x-intercept. And if you think about it, you can do the exact same thing with your y-intercept. It'll happen when x equals 0. So to solve for it, you set x equal to 0 and then solve for y. So what we're going to do on this next is we're going to discover an example problem and find all of these pieces so that we can eventually graph it. So here I have an example for you, and you'll notice that I've actually written it two different ways. One of the first things that you're going to want to do with this is if it's given to you in a factored form, you're probably going to want to multiply it just so that you can look at those degrees of polynomials. There is a way to look at the factored form and be able to see, so I can see there are two x's being multiplied, so the degree will be squared. But if you're not at that level and if you're a little unsure, you may want to go ahead and condense them and multiply them together. If they're given to you like this, it will actually be very beneficial for you to factor it because that's going to help you find different pieces of it. So I've gone ahead and factored them just so that we don't have to worry about that step, but factoring is very important to rational equations and a lot of other pieces of math, so it's a good idea to be able to do that. So we're just going to go ahead and go down that list. The first thing that we should look at is the horizontal asymptote. And the way we find our horizontal asymptote is by looking at those degrees. So I can see I've got a second degree polynomial in the numerator and a first degree polynomial in the denominator. So I have a second divided by a first, which tells me that my numerator is going to be greater than my denominator. That tells me, by the previous slide, that I have no horizontal asymptote. So right off the bat, we're good with our horizontal asymptote. The next thing that we're going to look at is, I said that to find the whole and the vertical asymptote, you're going to need to look at that domain. So I'm going to look at this equation, and I'm going to figure out what my domain is. The big thing that's going to come into play when you're looking at rational equations is that you're not allowed to divide by 0. So for this, since my denominators are the same in the factored form and the distributed form, it doesn't really matter which one I look at. But normally it'd be easier to look at the factored form. So if I want the denominator to not equal 0, then I'm just going to go ahead and take that whole denominator and say that it doesn't equal 0. This means that my domain is that x cannot equal 4. X is allowed to equal any number in the whole wide world except for 4. So there's my domain of the function. But if you notice, you could simplify this problem a little bit more. If I wanted to, I could cancel out the x minus 4 and the x minus 4, which leaves me with just x plus 4. Now, a lot of people are tempted to go ahead and cancel these out as soon as they see the problem, but you need to be careful. F of x is given as this function. As soon as you cancel something out, you've changed the problem. So if I asked you to graph the function f of x, and you cancel something, you're no longer graphing f of x. You're graphing something similar to f of x, but not equivalent to. So that's the key to where holes come in. You'll notice that in the simplified version, once I factor it out and cancel, I have canceled out my domain restriction. Now the domain of this function is all real numbers, which that tells me that I have a hole at this domain restriction. I have a hole at x equals 4. So this is the x position. If I wanted to find the y position for it, then I would go ahead and plug in to my now simplified form. So to find the actual point, I will plug into the simplified equation. So I'm going to go ahead and say 4 plus 4 equals my y coordinate. So I know that I'm going to have a hole at 4, 8. And I knew that there was going to be a hole because this restriction canceled out. Well, since that's the only restriction, that means I have no vertical asymptote as well. There are no restrictions that didn't get canceled out. So the last two things that I'm going to look at are my x-intercept and my y-intercept. So the x-intercept happens when y equals 0. So now I can actually make my life a little bit easier. I'm going to go ahead and use that simplified equation. I'm going to say 0 equals x plus 4. So I know that I'm going to have a y-intercept when x equals -4. So this is my x-intercept, and I can go ahead and write that as the point, -4, 0. In terms of the y-intercept, again, I'm going to keep my life simple. Remember, this yellow equation and this white equation are very, very similar, but they're not exactly the same. They're so similar that I can actually use this simplified version for these intercepts. That'll make the calculations a lot easier. So the y-intercept happens when x equals 0. So y equals 0 plus 4, which gives me y equals 4. So I've got a y-intercept at 0, 4. So these are all of the pieces to my graph. And what I've done is I've gone to a very popular graphing website called Desmos, and I have put in this equation, and I'm going to show you what that looks like. And we'll compare our answers to what the actual graph says. So here is the graph posted on Desmos. Let's go ahead and compare our previous answers. We found out that the horizontal asymptote, well, there was no horizontal asymptote. So as I look around at this graph, I can see that there is no horizontal asymptote. It actually just looks like a linear graph, and I'll explain why in just a moment. The domain was that x could not equal 4, and since that canceled out, that told us that there was going to be a hole at 4, 8. So if I actually scroll this over and I follow along to 4, 8, you'll see I always get values, I always get values, I always get values. But now as I get closer and closer to 4, everything is defined up until the exact moment I hit 4. And what's interesting is you'll see that it actually forms a hole like we drew in our definition. So this tells you that you've got a hole at x equals 4. It is undefined, and then as soon as I move past it, it starts becoming defined again. So if you were to zoom in on this graph a lot, you would find out that it is undefined and that there is a hole. Now Desmos is very, very smart, so if you try to zoom in on it, it'll actually populate those other values around it. So you'll never actually see that it's a hole unless you decide to hover over it and get to that undefined part. So there is the hole. You'll see that there aren't any vertical asymptotes either. And leading to the end, the x-intercept, where it intercepts the x-axis, is at -4, 0. So there's that x-intercept, followed by the y-intercept, which is 0, -4, right up here. So all of those pieces did match our graph very, very nicely. So now let's look at why it's a line. If you look back at the equation itself, you'll see that once things cancel out, it actually creates the equation y equals x plus 4, which is just a linear function. So this nasty equation here is equivalent to x plus 4, except it's got a hole when x equals 4. So if you wanted to, you could graph the line y equals x plus 4, and it would lay exactly on top of this graph, and the only difference would be the other graph is defined here. So having something that cancels in the numerator and the denominator will create a hole which could completely change the idea of the graph and the answers you receive from it. So let's take a look at our second example. Just like in the first one, we've got it split into the condensed version and the factored version. And that's going to make our lives a little bit easier in the future. So let's go ahead and start by looking for that horizontal asymptote. And the way we do that is by looking at the degrees of the polynomials. So again, the degree is the highest exponent on our variable. So we have a first degree in the numerator and a second degree in the denominator, which means that our numerator is a smaller degree than our denominator, which means we know we've got a horizontal asymptote at y equals 0. So this tells us about those end behaviors. Our end behaviors are going to get closer and closer and closer to 0 as we go farther towards negative infinity and farther towards positive infinity. The next thing we're going to look at is our domain. So the domain, as a reminder, is to make sure that the denominator doesn't equal 0. So you cannot divide by 0, which means the factored version of our equation cannot equal 0. And the way that this could not equal 0 is by saying, x plus 3, is by saying that x minus 3 can't equal 0, and x plus 3 can't equal 0. Doing a little bit of algebra says x cannot equal 3, and x cannot equal negative 3. So here are our domain restrictions. Once we find our domain restrictions, we are allowed to go through and see if anything cancels, which it does, and we are remaining with a very simplified version of 2 over x plus 3. Now that means one of our restrictions canceled. The restriction that canceled is this x minus 3 here. So this restriction creates a hole. We now know we have a hole at x equals 3. To find the y coordinate for that point, we're going to go ahead and plug in to our simplified equation. So when x equals 3, the y coordinate equals 2 over 6, which is 1/3, meaning we have a hole at the point 3, 1/3. Now that does mean one of our other restrictions did not cancel out, which tells us we've got a vertical asymptote at that location, at x equals negative 3. So that is a vertical asymptote because it didn't cancel out. It was a restriction in the beginning, it was a restriction at the end, which means it's that vertical asymptote. The last thing we want to look at is our x-intercept and our y-intercept. So the x-intercept happens when y equals 0. So just like we did to find our hole, we're going to go ahead and take that simplified equation and set it equal to 0. Now our goal is to solve for x in this equation, which x is in the denominator, so we would go ahead and multiply by x plus 3 to both sides. But when you do that, something weird happens, and you end up with 0 equals 2. Now because we're logical people, we know that this can never be true. This is just a false statement, which tells us that there is no x-intercept. And one thing to notice about that is we discovered there was a horizontal asymptote on that on that x-axis. So it's kind of okay that we have no x-intercept. As I said previously, it is possible to cross a horizontal asymptote in the middles. This just tells you about the end behavior, but this is a pretty good indication that it's okay to not have an x-intercept. It will not always be true that if this is your horizontal asymptote, we will have no x-intercept, but it supports that idea. So it's totally fine to not have an x-intercept. So let's go ahead and find our y-intercept when x equals 0. So y equals 2 over 0 plus 3, telling us that y is equal to 2/3, which means we have an x-intercept at 0, 2/3. So here is all of our information that we have. We're going to go ahead and graph it and see how that compares. So here is our graph of the function. One thing to notice is I've made it so that the actual graph is in green and the asymptotes are in blue. So normally you wouldn't see these asymptotes, but I've added them in just to kind of accentuate it and show you what's going on. So the first thing we found was a horizontal asymptote at y equals 0. So if you continue this graph off to the side, the green line will be getting very, 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 very close to the blue line, but never actually touch it. So that supports the idea of a horizontal asymptote in that direction. So now if I go over to the other side, you'll see it also gets very, very close but doesn't actually touch. So there we have a visual representation of our horizontal asymptote. The next thing we found was a hole at x equals 3. So as we look here, x equals 3, it looks pretty solid, but just like we saw in the previous one, you've got to actually scoot down to follow it. So we should have a hole at 3, 1/3. So as I get closer and closer to 3, you can see that y-coordinate is getting closer and closer to 1/3, which is 0.333. And you'll see right there, I've got it undefined. So there is a hole at x equals 3. And if we look a little to the left and a little to the right, it does appear that our y-coordinate is approaching 1/3. So awesome, we have our hole. A vertical asymptote at x equals -3. So here's our x equals -3. As I scoot up, you'll see it gets closer, and as I scoot down, you'll see it also gets closer and closer. So the very last things that we have to look at are those x and y intercepts. We are supported in the fact that we have no x-intercepts. Now looking at that y-intercept at 0, 2/3. So I get closer and closer to 0, you'll see I do in fact hit 0.667, which is 2/3 when rounded. So there we have it, our horizontal asymptote, our hole, our vertical asymptote, and our y-intercept with no x-intercept. Here is the third and final example that we're going to be looking at. At this point, I feel like you guys should be a little bit able to follow what's going on, and you should actually be able to do this one entirely on your own. So I'm going to encourage you to pause it and try and figure it out on your own. So hopefully you gave it a shot. Let's go ahead and take a look at all the different things we're going to be finding. First and foremost is a horizontal asymptote. So looking at the degree of the numerator versus the degree of the denominator, we see that we've got a second degree in the numerator and a second degree in the denominator, which means our numerator is equal to our denominator in terms of degrees. So that tells me it is a horizontal asymptote of y equals, and this is where I look at the coefficients, 3/2. So this is my horizontal asymptote. Let's go ahead and jump over to domain. So the domain, again, is the denominator cannot equal 0. That is the big one for rational equations. So x minus 2 times 2x plus 3 cannot equal 0, which means x minus 2 can't equal 0, and 2x plus 3 can't equal 0. Again, a little bit of algebra says x cannot equal 2, and x cannot equal -3/2. So there is our domain. Let's go ahead and find out if anything cancels out, which it does, leaving us with a simplified version of 3 times x minus 6 over 2x plus 3. Because something canceled out, we know that we do have a hole. So here we have a hole at, well, this is the one that canceled out, so a hole at x equals 2. Let's go ahead and find that y-coordinate. So 3 times 2 minus 6 over 2 times 2 plus 3. So I'm going to do this in steps to make sure I don't make a silly mistake. So 3 times -4 divided by 4 plus 3. So -12/7, which is a really disgusting, nasty number, but that's the way it works out sometimes. Math isn't always nice, pretty, even integers. So we know we have a hole at 2, -12/7, which for those of you that are curious, to write that in decimal, because we're going to be looking at it on the graph, is 2, -1.714. So there is something that didn't cancel out, which tells me we have a vertical asymptote at x equals -3/2. Which leads us to the very last bit, the x and the y intercepts. The x-intercept is when y equals 0. So I'm going to take my simplified equation, set it equal to 0, times 3x minus 6 divided by, a little bit too far, divided by 2x plus 3. multiply both sides by 2x3 to eliminate that denominator, and we end up with 0 equals 3 times x minus 6. A little bit more algebra, divide by 3 and add 6. So 6 equals x. We have an x-intercept at 6, 0. So all of these are leading into it with just a little bit of algebra steps there. Finally, our y-intercept is when x equals 0. So y equals 3 times 0 minus 6 divided by 2 times 0 plus 3. So simplifying a little bit, and again I'm going to do it in steps like I did with the whole to make sure I don't make a silly mistake. 3 times negative 6 divided by 3. Well, those 3's cancel out, and I am left with y equals negative 6. So this right here tells me that I have a y-intercept at 0, negative 6. So here's all the information that we've got. Again, just like the last two times, we are going to go ahead and plug this into Desmos and see if our information is supported by the graph. Here we are for the last portion of the graph, last portion of the video. Just like last time, I've got green is our actual graph. This time I made the asymptotes dotted lines to help you see that it is in fact imaginary. They don't actually exist. It is the idea of them that exist. So the first thing is horizontal asymptote at y equals 3/2. So you'll see this is the equation 3/2. And you can see as we go farther and farther to the right, green will get closer to blue but never actually touch it. And then off to the left, same thing. Green will get very, very close to blue but never actually touch it. So there's our horizontal asymptote at 3/2. We should have a hole at x equals 2, and then it should be 2, negative 1.7. So as we get closer and closer to 2, you'll see, there we go, we've got a hole, and it is at approximately 1.719. So there we are with our hole. Awesome. One more down. Looking at the vertical asymptote when x is equal to negative 3/2. So here's that line. X is equal to negative 3/2. If I scoot down, we will get closer and closer. And then if I scooch up, again, we'll get closer and closer. So there's that. Last two things are the the x-intercept and the y-intercept. X-intercept we said was at x equals 0. There it is. And then the y-intercept we said was at negative 6. There we are there. So we have got our intercepts, we've got our asymptotes, everything is in line. So that stuff that we did to prove those components actually shows up in the graph as well.